This is Official Nerd Business.
Hello nerd boys and girls, welcome back to another Euler Problem. Today we are using Python 3 in the PyCharm IDE to take a crack at problem number 38. The problem states it's about Pandigital multiples. The problem states take the number 192 and multiply it by each of 1, 2 and 3. By concatenating each product we get 1 to 9 Pandigital, namely 192 from the times 1, 384 from the times 2 and the 576, which makes all the digits from 1 up to 9 appear exactly once, which is, as we've seen in previous challenges, the definition of being Pandigital. Pandigital, it's not really explained in this challenge. Pandigital means that each digit, it's 1 to 9 Pandigital, so each digit including from 1 to 9, including those both those extremes, appear exactly once in the result that we want. We will call 192 etc. the concatenated product of 192 and 123. The same can be achieved by starting with 9 and multiplying by 1, 2, 3, 4 and 5. When I first read this, I was pretty much amazed. So multiplying 9 by 1 through 5 gives us a Pandigital product. 9, obviously, multiplying 9 by 2 gives us 18, and 27 and 36, then 45. So, kind of logical once you stop to think about it, but seeing it stated like this, it's pretty amazing. What is the largest 1 through 9 Pandigital 9-digit number that can be formed as the concatenated product of an integer with 1, 2, and n, where n is greater than 1. Note that the n is greater than 1 catch here is so that we don't just take 9, 8, 7, 6, 5, 4, 3, 2, 1, multiply that by 1 and there you have it. So we need to multiply a number by 1 and by 2 and at least by 2 and possibly by 3 and maybe by 4, and as we've seen it works for 5 too, but that's in the single digit numbers. And then all the results rolling out of that, we need to concatenate them, check if that's a Pandigital product, and check which is the highest we can reach. So a lot to take in here. I've already created all of the boilerplate code as I usually do. And I think we're going to start by creating a function that does all the calculations for us, all the multiplications, and storing all the intermediate results. And let's call this Pandigital product maker. Why not? For any given n. In a little bit we're going to fill in temp number 1, and as you can see in this boilerplate code it calls temp number 1 whether we from the run method, and the run method can be called either from our main py or on its own in this bit. This also transfers control to the run method. Alright, let's see. We want to keep track of all the digits and we want to concatenate things to them. That to me says string more than it does integer. So we're gonna we're gonna have a string value here to store things in. Also, in fact, let's call this an x, because the n, I want to keep this n in here, because the n is used to indicate an element in this series. So I want to have the input number here. If for instance we're going to put the 192 in here, that's going to be called x, not n. And n is going to start off at 1. And then we're going to set up a simple loop while the length of s is less than 9, because once we do reach 9 or overshoot 9, both can happen, then we know we need to evaluate the string to see if it's Pandigital. And as long as we are not there yet, we are going to concatenate to this our x times our current n value, and we are going to increment n by 1. Then this is gonna roll out of here again, and now we're gonna check if the length of S is exactly 9. If it's not, by the way, we're gonna return an empty value. And in the calling function, we're going to check if this is empty or not. And if it is not, this is going to have a Pandigital string in it. So for instance, from the example of 9, this is going to hold 9, 18, 27, 30, etc, etc. But if it isn't Pandigital, then it will return an empty string. We're going to deal with those in the calling function a little later on. And now we want to check if this is Pandigital. And I think for that we're going to take all of its characters and sort them. And the fun thing is we can just sort any string. There's the sorted function, which does the sorting for us on an iterable, and a string is considered iterable, and it will just yield a list of all the characters in their ordered form. So we have S here. However, this is now a list, and we want to check if it equals this string. Now we could blow this into a list, or we can make this into a string by using the the join function. Now note that I've set this, I'm going to in fact return this. I've set this before in many other programming languages. The join would be a method that you would call on a list. So there would be a list variable here, dot join, and then you'd get a string, and it will then join all of the list elements, combining them, concatenating them to one string, and using this string as a filler between elements. In Python's case, this is reversed, so you get the filler string and you tell it to use this particular filler string to take this here list, get all the elements, concatenate them using the filler string. By using the empty string, we will not get any fillings. We will, however, see all of the elements of our list, and all of the elements of our list are sorted. So if this condition is met, then we return the actual string that was made by using this. And otherwise we will return an empty string. Test early, test often, so we're gonna print a couple of known test cases. This one is given to us in the example. As is 9, and we can safely assume that 10 is not going to be 1, because 1 times 10 is 10, 2 times 10 is 20. Concatenating this, first of all, we are not interested in zeros in our number, and second of all, we would have a double zero. Third, ignoring the zeros, we would get a 10-digit number at some point instead of a 9-digit number, and ignoring that, it would only have the digits 1 through 5 instead of 1 through 9, ignoring all the zeros and trunking into 9. So yeah, we can safely assume that 10 is not going to join our part here, but I want to show what this function does when that happens. So we're going to run this particular file, not through main.py, we're going to run this to see if our Pandigital product maker does what it says in the bottle. And it does not. Right, because I forgot to cast this to string. I am trying to append a number to a string here, and it's having issues with that. But that's on me, Python, please forgive me. And there we have it. These are the exact test cases that were given to us by the project Euler's description. These match, and there is a third one here which is just a blank string. Alright, so how are we going to harness this? Well, simply for I in range, I'm going to start at I'm going to start this loop at 10, and we're going to loop all the way up to, let's see, we're going to concatenate at least 2 numbers. So we're going to multiply, we need 9 digits, so if we do this, 1, 2, 3, 4. No wait, 1 0 too many. We're going to run up to, but not including, a 5-digit number, because the 4 9s times 1 will be 4 9s. 4 9s times 2 will give us a 5-digit number. Together is 10 digits or 9 digits, and anything else would exceed that from the get-go. Let's also, our maximum Pandigital product is a blank string. Then if I'm going to quickly store what we are generating here. Now I'm going to start at 10. We saw that 9 works. We can safely assume that nothing below 9 works. And the problem statement specified that we are looking for a number that's the largest Pandigital product, and they're not going to give that away in the example here. So the 9, although it does generate something with a lead 9, will not be the highest that we can reach. So that's why the loop starts at 10 and not at 9. Or if it started at 9, by the way, and then this would be filled with something quite high immediately off. That's fine. Let's see, we now get this, and if temp is not an empty string, or in fact if temp is greater than, note that we are guaranteed to get a 9-digit string here, so the greater than comparison works equally for strings as it would on numbers. And then we hit the next iteration, and then we are going to return this one. Now I want to ensure that we hit the run method, but we are going to do so through main by, I think. Yes, let's kick off main by. Let's see, problem number 38. There is no input, so we're going to jump right into it. And there we have our answer. If you enter this number over at project-euler.net for problem number 38, you will get a green check mark, and it's pretty quick. But it's problem, I think we've brute forced this a bit, quite a bit. We've done absolutely nothing to reduce our possible search range, while I think that if you sit down with a pencil and paper, you can get this whittled down quite far. So I'd like to take a look at how you might go about reducing the search area effectively of where our Pandigital products could be hiding. So let's have a look. Let's get ourselves some pen and paper. Alright, Pandigital products. We've just seen the problem description. So what do we know? What, just by simply looking at this problem, can we use to reduce our search area? The formula, as you've seen, is repeatedly appending to an already existing string whatever string comes out of multiplying our x with the next n. S is a string with all the concatenated digits. X is some base number. If we take a look at the first example in the project Euler's description, then that was 192. And n is 1 at first, then 2, and possibly more. We are the problem statement requires us to look at least 2 values for n, starting at 1, so 1 and 2 are a given, possibly more. We need 9 digits. To make this Pandigital, we need all of these digits exactly once, so that's 1, a 2, a 3, 4, 5, 6, 7, 8, 9. And as long as S is less than 9 digits, we increase n, we multiply, and we do all of this again. We can't use single digit numbers. Now we can, but we know that we can do better than anything given by single digit numbers. Alright, I'm sorry, this shouldn't say we can't use single digit numbers. This is something in my head when I type this. This is related to n, we need at least 2 n's, never mind. But we do know that because the 9 itself as an input x was given as an example, we can do better than that. And we need the biggest result, so if possible a 9 should go out in front. Well, we've already seen from our brute force approach that we will find something with a 9 out front. So when we are given 9 digits as the result of at least 2 multiplications, let's see when we have 9 digits. So here's a little bit of a multiplication table. We already saw that the 9 itself, single digit, works. I have set up a mock-up value for x. We want a 9 in front, so the first term needs to be either 99 or 98 or 97 or whatever up to down to 90, or 900 up to 999, or 9000 up to 1 less than 10,000. And we're going to multiply that by 1, 2, 3, 4, and we're going to check if the length of 1, 1 plus 2, 1 plus 3 is or exceeds 9. So the multiplication table for 90 is 90, 180, 270, 360. And keeping track of how many digits we have is 2. 2 plus 3 is 5. Another 3 is 8, and then we hit 11 digits. So there's no 9-digit number for 90. Now, do we get any rollovers with more digits? We don't. We would only get those rollovers for values of 50 or for values of 33 in the 34, 33 and a bit. So no rollovers, or in fact we do have a rollover, but we only have one. If you multiply a 2-digit number by a 1-digit number, you are guaranteed to get only 2-digit numbers or 3-digit numbers back, and we have the rollover already here. So there's no. That's why I picked the 2 extreme values in this range to check this out to see if there is any rollover, but there isn't. So you get the exact same stats here as you do for the others. The 900 is equal to the 999, and the 9000 is equal to the 10,000 minus 1. So if you have a look at the results of our table here, we have 3 digits in total, 7 digits in total, and then overshoot it with 11 digits. And we have 4 digits in total, 9 digits in total, and then 40. Oh, wait a second, we have 9 digits. So there might be candidates hiding in the 9,000 to 9,999 range. So let's go look if we can find those. Alright, let's see. We've reduced our search area and we've also seen something else. In fact, we haven't explicitly seen it, but maybe you figured this out by yourself by now. If we take the range in reversed order, we can quit early. If we find we are going to look between 9,000 and 999, etc. And once we find one, if we start looking at, if we take a look at this, obviously this isn't going to be it, but this could be. I'm not saying it is, but could be. Then if this, with its second iteration, happens to hit any Pandigital number, we know that there will not be any higher Pandigital product possible, because the very next number would have its iteration 1 start out lower than this. So this is guaranteed to be a winner. So we can quit early on that. We don't need to track which is currently the highest. Once we find one, we know that we have a winner. So we're going to do that for I in range. We're once again going to take this temp value here, and if temp is unequal to our blank string here, return temp. And if we do manage to fall out of this loop, returning none in this case would be the best solution to indicate that this function did not yield the expected results. And we are going to run attempt number 2. So let's hit off makepy again. Oh wait, made an error here, didn't tell the range object to descend. So it immediately dropped out of the for loop here without ever doing any calculation. My bad. Problem number 38. And even though we had a great runtime the first time round, we've reduced that by an entire order of magnitude. So here we have the same answer again, as you can see, since we are looking for numbers between in the fourth order of magnitude. We know that the lead number is 4 digits long, and the resulting, so the N2 gives us this 18,000 whatever number here. So you can kind of read that back. Now you know what digits belong to this N1 case and what digits belong to the N2 case. So that's informative, I guess. So there's that. As said before, it's kind of a shame that this problem is so easy to brute force. Just sitting down and thinking about how we can make the target search area as small as possible, and whether or not we need to keep track of intermediate results or know that once we find something, we did find the actual maximum. I think those are the fun elements in this problem. I hope you've enjoyed them, and I will see you again next time for problem number 39. Thanks for watching this video on Official Nerd Business. Don't forget to like and subscribe and click the bell icon. Did we discuss everything you wanted to hear, or did we miss anything? Any topics you want to hear in O&B? Leave your thoughts in the comments. See you next time.